The exponential function can be written in this infinite series, but if we were to actually compute the exponential function, we can't really add up an infinite number of terms. Instead, we have to stop computing the terms somewhere and ignore the terms later on in the series, hoping that all the terms thereafter are so small that it doesn't really affect the result much. However, where should we stop in this series? How many terms do we really need? Now, this question is still a bit vague, so let's say we want the terms we computed to be like 99% of the answer, and the terms we ignored occupy only 1% of the answer. You can of course not be satisfied with just 99% accuracy, but for now let's just settle for 99%. So our problem is, when will we have 99% of the answer when adding the terms in this series? In this video, we focus on the case when x is a very large integer. We could start investigating by constructing some sort of histogram. For example, the 0th term is represented by the leftmost bar, which would have the value of 1, or x to the 0 over 0 factorial. In general, we want to draw the kth term in the series for the histogram. If we in addition make the width of each bar to be 1, then the area of each bar is x to the k over k factorial. So if we add up all the areas of the bars, the total area is e to the x. The histogram shows roughly where we should stop computing. For the terms on the far right, the contribution is negligible and we could just stop around here. However, if we insist on this being the height of each bar, without any normalization, then by increasing the value of x, there is going to be a huge problem. As we increase x, the bars quickly go beyond the scale, and we could not really see a lot. Okay, so we go back to the original histogram and now just scale everything so that the highest bar is capped here. What will happen as we crank up the value of x? Well, now we have run into another problem. The peak moves and we can't see very well again. Well, okay, let's go back to the original histogram again and try to not only limit the height, but also scale the width of the bars on screen to fix the peak of the histogram. Surely this will work now as we increase the value of x. And it does work. But have you noticed the pattern as x grows? This is now a bell curve, which is the characteristic of a normal distribution. Hang on, what is normal distribution doing here? Let's see how. We now go back to this original problem. We want the terms we computed to occupy the vast majority of the answer. One approach is to see the proportion that each term contributes to the series. For the kth term in the series, the proportional contribution is x to the k over k factorial out of the full e to the x. This can be written as e to the negative x times x to the k over k factorial. Does this expression look familiar? If you watch my previous video, you will notice that these terms form the Poisson distribution. It is used to describe the probability that if on average there is a rate of lambda customers coming in, where the customer arrivals are independent from each other, then the probability of exactly k customers is e to the negative lambda times lambda to the k over k factorial. From the connection with the Poisson distribution, we can rephrase our problem as, when we consider the possibility of more and more customers coming in, at which point would the cumulative probability be larger than 99%? Because of the connection with probability, the previous observation of the bell curve or normal distribution might make you scream, "Central limit theorem!" Yes, that's related, but we have to be careful in how it is related. The statement of the central limit theorem is that if we have n independent copies of the same random variable, all with the same mean mu and variance sigma squared, then there is this statement, which means that we first consider the difference between the empirical average and the theoretical average. After we scale the difference by multiplying by square root of n, then for large n, this scaled difference follows a normal distribution. But let's forget the final result for a minute. If we want to use the central limit theorem, we have to first create these copies. How can we do it? What we have is just one Poisson variable that follows the Poisson distribution. However, if the probabilities correspond to the arrival process of customers at a rate of lambda, it is possible to split it up into several independent ones. And as long as the arrival rates sum to lambda, the total number of customers in the system would have the same distribution as the original unsplit one. Another way to look at it is that let's say we have customers arriving at a large store at a rate of n per hour, with n being an integer. An alternative way that this can be achieved is that there are n different departments in the store, and the customers arrive at each department at a rate of 1 per hour. If we denote x as the total number of customers going into the store in an hour, then x follows that Poisson distribution with rate n, giving probabilities e to the negative n times n to the k over k factorial. And if we denote xi as the number of customers arriving at the ith department in an hour, then these xi's will also follow the Poisson distribution, but with rate 1, giving the probabilities as e to the negative 1 times 1 to the k over k factorial. Now the argument that we can split this up into n different arrival processes means that the x and the xi's have the same distribution. In other words, the probability that x equals a certain number m is the same as the sum of these xi's attaining m. This argument is quite intuitive, but might not be completely convincing to some people, and that's completely understandable. After all, these two situations are not entirely equivalent. We can prove this even more precisely. More generally, if we have two Poisson processes with rates lambda and mu respectively, and denote x and y to be the number of customers for the respective processes, then the probability that the sum of these two being n can be computed by summing all the possibilities of x and y. If one of them is I, then in order for the sum to be n, the other process has n minus I customers coming in. The next step is to substitute the Poisson distribution formulas for x and y, and then try to sum these up. The penultimate step involves just a little rearranging of the expression inside the summation. The exponential parts gets combined together, and we add 1 n factorial in the denominator and 1 in the numerator. And then finally, we can use the binomial theorem to conclude that the boxed expression is lambda plus mu to the n. But now, the final result again follows the Poisson distribution, just that this time, the rate of arrivals is lambda plus mu. This means that the overall process is really the Poisson process with the combined rate. So hopefully the calculation makes it much more convincing, albeit a little tedious. In any case, the idea is that if we want to use the central limit theorem, we can split up this high rate of customer arrivals into n different arrival processes, each with a rate of 1 customer per hour. And with that, let's go back to the statement of the central limit theorem. In this case, we want the identical copies to be the Poisson processes with rate 1. They will follow the Poisson distribution with both mean and variance being 1. The mu and sigma squared can be substituted into the final statement of the theorem. But what does this statement translate to? This means that the probability that the quantity is smaller than m becomes more and more similar to what a standard normal random variable does. Our next task is to massage the expression inside the probability. Remember that each of these xi's represent customer arrivals at a rate of 1, and we said that the sum is equivalent to the arrival process with rate n. So as n tends to infinity, we have this statement about the Poisson distribution only because we can split it up into n different small arrival processes. Now, Poisson distribution tells us that the left-hand side is the contribution of the first m times square root of n plus n terms in the exponential series. So, if you want these terms to contribute 99% of the exponential series, then we just need to find the m to be in the top percentile of the standard normal distribution. In general, there is no closed form formula to find that out, and we have to do this numerically. In this case, we need the m to be around 2.33 so that we get a 99% cumulative probability. That means for the probability to reach 99%, we need m to be about 2.33. This in turn means that for large n, we need roughly n plus 2.33 times square root of n terms in the series to reach 99% accuracy. So what we have demonstrated here is that if you want 99% accuracy, then n plus 2.33 square root of n terms are required in the series. And if you want even higher accuracy, then you will need more terms, but the number of terms required is also similar, like n plus something times square root of n. To put this to scale, let's say we want to compute the exponential of 1,000. The number of terms required are roughly in the order of 1,100, and that's quite a lot of term required already. But what's more, during the exponential series, each term is very difficult to compute. The numerator is totally fine, it will just be 1 with a bunch of zeros, but the denominator is really difficult to compute. So if you want to compute the exponential of a large number, adding up terms in the series is very, very inefficient. So how do computers actually compute the exponential function? You can head over to Oscar's channel to find out. He does a lot of different videos on numerical methods, or you can click the card above. In any case, if you enjoyed the video, please like and subscribe with notifications on, comment and share the video. It will help a lot. See you next time!